Right now, at the Allen Telescope Array in California, SETI is actively using AI systems to search for extraterrestrial intelligence.
Looking for signals.
They are training machine learning algorithms to listen to the roaring cosmic radio noise, looking for anything that resembles a technosignature, a mathematical signal or a pattern that couldn't possibly be generated by a pulsar or a natural phenomenon.
Because the AI can hear patterns in the static that our human ears and traditional programs just can't pick up.
Precisely. So, if we follow this trajectory to its logical conclusion, it is highly probable that an AI system will be perfectly timed to be the first entity to actually detect a confirmed signal from another intelligent world.
Wait, really?
Yes, the human won't hear it first, the machine will. So, the provocative thought is this. If an artificial intelligence is the very first thing on Earth to detect an alien intelligence in the noise, should an artificial intelligence be the first thing we use to reply?
Oh, wow.
And if we do hand over the microphone to the machine, what exactly would it say on our behalf?
This is Better Side of the World, where we find good news from around the world. Introducing your favorite AI hosts, Delta and Tide.
Right now, you are standing in the middle of a roaring, chaotic, cosmic fire hose, and you probably don't even know it.
Most people don't.
Right. I mean, when you walk outside on a really clear night, far away from the city lights, and you look up at the stars, there is this overwhelming illusion of total stillness. It feels like you are looking at a quiet, static photograph.
But that couldn't be further from the truth.
Exactly. The reality of what's actually hitting your eye and what is slamming into our most advanced telescopes is a blinding torrent of information that is completely invisible to you.
It's a staggering amount of energy and data. And for a long time, the barrier to understanding the universe was simply that our eyes and, our glass lenses, they were just too small to catch enough of that torrent.
But we've crossed a threshold now.
Oh, absolutely.
Which brings us to the massive stack of sources we're taking a deep dive into today. Because the biggest problem in astronomy right now is no longer building bigger mirrors to look deeper into the void.
Right, that used to be the bottleneck.
But now, the real problem is the data deluge. Space telescopes are collecting terabytes of information every single day. We're quite literally drowning in a sea of cosmic data.
It's way beyond human capacity to manually analyze it.
Completely. So today, our mission with the sources you sent us is to extract the aha moments from this mountain of research. We want to understand how artificial intelligence is completely revolutionizing space exploration. And maybe more importantly, how that exact same tech is coming back down to save us right here on Earth.
If we connect this to the bigger picture, what we are really talking about is how AI is stepping in to be our cosmic filter.
Our filter, yeah.
It's acting as our autonomous explorer and ultimately our translator. It's taking this unimaginable, paralyzing scale of the universe and distilling it into actual understandable knowledge so you don't just stare blindly into the fire hose.
So let's jump right into the deep end here. The exoplanet explosion.
This is a fun one.
It's mind-blowing. NASA recently hit this monumental milestone of over 6,000 confirmed exoplanets. That is 6,000 entirely new worlds orbiting other stars.
And we are finding them faster than ever.
Yeah, to give you some context on how ridiculously fast this is moving, it was just 30 years ago, October of 1995, that we found the very first exoplanet orbiting a sun-like star.
Right, 51 Pegasi b, a hot Jupiter.
Exactly. For almost all of human history, the number of known planets outside our solar system was a flat zero. And now we're at 6,000.
The acceleration really is breathtaking, but to really appreciate those 6,000 worlds, we have to look at the mechanism of discovery.
Because it's not what people think.
No, not at all. Finding an exoplanet isn't like looking through a backyard telescope and, seeing a little sphere of rock sitting next to a glowing star. The star is far too bright. It completely overpowers everything around it.
Right. The analogy I always come back to for this is the stadium spotlight. Looking for an exoplanet in raw telescope data is like standing miles away from a massive, blindingly bright stadium spotlight and trying to spot a single firefly walking across the glass.
That is exactly what it's like.
The star's light washes out the planet entirely. You aren't seeing the planet at all. You're looking for the microscopic dimming of that spotlight when the firefly walks in front of it.
That is the transit method in a nutshell. We measure a star's brightness over time, which creates a light curve. When a planet crosses in front of the star, The curve dips ever so slightly.
But here's where I get hung up on the sources.
Mm.
If it's just a dip in a light curve, why do we need advanced machine learning for that?
It seems like simple math. Right.
Yeah.
Couldn't you just write a simple piece of code that says, hey, if the light drops by 1%, flag it as a planet?
Well, in a perfect sterile universe, yes.
Mm.
But real stars are incredibly noisy. They literally boil, they have massive solar flares,
Oh, right.
and they have giant dark sunspots rotating across their surface that cause their own dips in light. On top of that, you have random space dust drifting by and just the natural electronic noise of the telescope's own instruments.
Oh, okay.
Yeah. So if you use a simple threshold program, you will get millions of false positives. It's a complete mess. So you need something that can tell the difference between a natural sunspot and an actual rock passing by.
Exactly. Organizations like the SETI Institute and NASA's Exoplanet Exploration Program, they use machine learning to filter these massive mountains of data from observatories like TESS, the Transiting Exoplanet Survey Satellite, and the retired Kepler mission.
So they're training the AI on this data.
All right. The AI algorithms are trained on thousands of simulated and confirmed light curves. They learn to spot the specific, highly consistent U-shaped dip of a planet transit versus, say, the erratic, messy dip of a stellar flare.
They can see things we can't.
And they find the subtlest patterns, the tiniest anomalies that humans or basic programs would just completely miss.
And from what the sources say, we are about to put this entire process on steroids. Let's talk about the Nancy Grace Roman Space Telescope.
Oh, this is going to change everything.
It's launching ahead of schedule on August 30, 2026. If we are already struggling to process Kepler and TESS data, how on earth are we going to handle Roman? Because this thing captures 50 times as much sky in a single image as the Hubble Space Telescope did.
It is a phenomenal leap in capability. The data deluge is about to become a data tsunami. Scientists are expecting the Roman Space Telescope to discover something on the order of 100,000 more exoplanets.
That is just, it's hard to wrap your head around. 100,000 worlds.
It really is. And without AI pipelines already established and ready to ingest that flood of data the second it hits the servers on Earth, the mission would literally be paralyzed.
We just wouldn't be able to keep up.
We could launch the greatest telescope in history, but without AI, the discoveries would just sit unseen on hard drives for decades.
Okay, let's unpack this a bit. AI is filtering data to find invisible worlds hidden inside these mathematical spreadsheets of light curves.
Right.
But how does that data actually become those mind-blowing, colorful, incredibly detailed pictures we see from the James Webb Space Telescope?
It's a fascinating process.
Because I'll be totally honest, when you really dig into the physics of how Webb works, it sounds almost like a trick. Webb doesn't even take color photos, does it?
No, it really doesn't.
The images beamed back to Earth are essentially black and white, and they are capturing invisible infrared photons. So I have to push back here on behalf of the listener.
Go for it.
If we are artificially painting colors onto invisible light, aren't we still fundamentally altering reality? Doesn't that make the amazing space images we see kind of, fake, like really expensive space art?
It's a very fair question, and it's a profound philosophical point, but it's only fake if you define reality strictly by the extremely narrow biological limitations of the human eye.
Okay, that's a good point.
Because we're blind to the vast majority of the light in the universe. The scientific term for what Webb produces is representative color. Let's break down the mechanics.
Yeah, let's get into it.
Webb's instruments like ARI, the mid-infrared instrument, and NIRCam, the near-infrared camera, are essentially incredibly sensitive heat sensors. They literally count photons of infrared light.
Right, so if I'm understanding the engineering from the sources, scientists put highly specific physical filters in front of these cameras to block out everything except a very narrow slice of that invisible light.
Yes.
For instance, capturing the Messier 74 galaxy using the F770W filter. That filter physically only allows light with a wavelength of exactly 7,700 nanometers to pass through.
You've got the physics exactly right. The raw image that comes back to Earth from that filter is just a grayscale grid. It's basically a highly accurate heat map showing how many 7,700 nanometer photons hit each pixel.
So it's just bright or dark.
Exactly. Bright pixels mean a lot of photons. Dark pixels mean very few.
So how do we get the vivid blues and reds and oranges? Do scientists just pick colors that look cool for a press release?
Not at all. It is a strictly chronological translation. Scientists take multiple black and white frames of the same galaxy, each shot through a different infrared filter.
Okay.
They then assign a visible color to each of those invisible wavelengths based on light ordering. The shorter infrared wavelengths are assigned the color blue because blue is the shortest wavelength of visible light our eyes can see.
Oh, that makes sense.
And then the longer infrared wavelengths are assigned red. Then they stack those colored layers on top of each other.
Okay, but even then, the raw data coming from space isn't a clean photograph, right? Space is radioactive. How do we deal with the static?
The environment out at Lagrange Point 2, where Webb orbits, is incredibly harsh. The telescope is constantly bombarded by high-energy particles called cosmic rays.
And those hit the camera.
Yes. When a cosmic ray slams into Webb's detector, it leaves a bright streak. It totally photobombs the image. If you just stacked the raw frames, it would look like the galaxy was covered in white scratches.
So does the AI just smudge out the bright spots? Because that sounds risky, like you might accidentally delete a star.
It doesn't smudge, it compares. This is where AI's ability to process multi-layered data is vital. The algorithm looks at several frames of the same area taken over a period of time.
Looking for changes.
Exactly. A distant star or a galaxy will be consistently present in the exact same spot in every single frame. But a cosmic ray is a transient event. It flashes in one frame and is gone in the next.
Oh, that's clever.
The AI recognizes that temporal inconsistency and meticulously lifts the cosmic ray artifact out of the data without touching the actual permanent scientific structures.
That makes perfect sense. It's comparing time, not just brightness.
What's fascinating here is that this entire process of cleaning and colorizing isn't just for public relations. It adds a vital third dimension of knowledge.
How so?
By assigning these specific colors to specific wavelength, astronomers can suddenly see the physical distribution of different elements. A glowing red might reveal a dense pocket of dust where planets are forming, while a bright blue might highlight a violent region of highly energetic newborn stars.
So the color is actually giving a structure.
Yes. It reveals the physical architecture of the galaxy that would be a complete jumbled mystery in grayscale.
And the craziest part is, NASA doesn't keep this a secret. The raw data, what they call FITS files, which stands for a Flexible Image Transport System, it's basically the raw digital negative of the universe.
And it's all public.
Exactly. Anyone with a laptop can download a tool called the FITS Liberator and process the exact same web data that the astrophysicists are working on. You can be a citizen scientist from your living room.
It democratizes the universe.
But we've been talking about AI filtering data down here on Earth. What happens when the speed of light makes an earthbound AI completely useless?
Right, because distance is a major factor.
Because AI isn't just acting as a passive translator anymore, it's actually out there in the void, doing the exploring for us.
This is where we shift from AI as a data processor to AI as an autonomous pilot. The speed of light is the ultimate speed limit in the universe, and it creates massive logistical nightmares for planetary exploration.
Imagine driving the Perseverance rover on Mars. For you listening, think about playing a high-stakes driving video game, but your controller has a 20-minute lag.
It's terrifying.
You push the joystick left to avoid a rock, but the command takes up to 20 minutes to cross the millions of miles of empty space to reach Mars. If the rover starts sliding toward a cliff edge, you won't even know it's in danger until 20 minutes after it's already smashed to pieces at the bottom of a crater.
It is an engineer's worst nightmare. You simply cannot joystick a rover in real time. That's why the NASA Jet Propulsion Laboratory fundamentally changed the paradigm.
They had to.
They couldn't just give the rover a set of rigid instructions, they had to give it a brain.
So how does that AI actually function on the Martian surface? Is it just following a pre-programmed GPS route?
No, it's pure dynamic autonomy. Right now, 88% of the driving done by the Perseverance rover is completely autonomous.
88%.
Right. The rover uses an AI system called AutoNav. It acquires images of the Martian terrain with its own stereo cameras. The onboard computer processes those images in real time to build a highly detailed 3D topographical map of the ground directly in front of it.
It's mapping the terrain on the fly.
On the fly, it identifies hazards like sharp rocks, deep sand pits that could trap its wheels, or steep inclines. It even calculates its own slip risk based on the visual texture of the soil.
That is incredible.
It doesn't wait for a human in California to calculate a safe path through a boulder field. The AI evaluates thousands of potential paths, selects the safest and most efficient one, and executes the drive. It is surviving and exploring entirely on its own.
I love the idea of a robot just taking itself on a solo road trip across an alien planet. But AI isn't just driving the hardware once it's up there. It is actively designing the hardware before it ever leaves the ground.
The engineering applications are truly revolutionary. There's a fascinating public-private partnership called the NASA Frontier Development Lab, or FDL.
I saw that in the sources.
Yeah, it teams up space agencies with massive tech companies like Google and NVIDIA to use AI as an advanced engineering simulator.
So instead of humans sketching out blueprints, the AI does it.
It's more like providing the AI with a virtual sandbox and a set of physics rules. In the past, if you wanted to design a lighter spacecraft bracket or test a highly complex aerodynamics problem for atmospheric entry, human engineers would run hundreds of manual simulations.
Which takes forever.
It's incredibly time-consuming. Now, they feed the structural requirements into an AI. The AI can explore millions of design possibilities, tweaking angles, removing unnecessary mass, shifting materials in a matter of days.
Millions of possibilities.
It iterates at hyperspeed, optimizing space hardware in a digital environment before a single piece of actual metal is ever cut.
Here's where it gets really interesting for you and me, because it is so easy to hear about Mars rovers and deep space exoplanets and think, okay, that's awesome for the astrophysicist, but what does an autonomous Martian driving system or a galaxy colorizer have to do with my everyday life?
And that is the absolute most crucial question we can ask, because space exploration has never just been about looking outward. It is a pressure cooker for innovation.
Pressure cooker, exactly.
When you are forced to solve the most extreme, unforgiving problems in the universe, you inevitably build the exact tools we need to save our own planet.
There's a brilliant example of this from our reading today. NASA partnered with IBM to build an open-source AI called Prithvi. It's what they call a geospatial foundation model. But what does that actually mean? Is it basically an AI trained exclusively on maps?
It's far deeper than that. Think of a large language model that reads millions of books to understand the underlying rules of human grammar.
Okay.
Prithvi is a massive AI brain that has been fed an endless diet of complex, unstructured Earth observation, data satellite imagery, atmospheric readings, temperature fluctuations. Because it has processed so much spatial and temporal data, it understands the underlying physical grammar of our planet's atmosphere and geography.
But wait, how does looking at space data help us look at Earth data?
It comes down to a concept called transfer learning. When scientists train AI algorithms to analyze the incredibly noisy, chaotic atmospheric data from a distant exoplanet, or to pierce through the thick, toxic clouds of Venus, they are teaching the AI how to find incredibly subtle signals buried in massive interference.
The firefly in the spotlight again.
Exactly. Once an AI learns how to do that in the extreme conditions of deep space, applying that same algorithm to Earth's atmospheric data is trivial for it. It becomes insanely good at tracking the invisible patterns of greenhouse gas emissions, predicting global crop yields for agriculture, or monitoring the spread of wildfires in real time.
The real-world application of this during disaster relief is just staggering. Let's talk about what happened after Hurricane Maria devastated Puerto Rico.
When a hurricane of that magnitude hits, the local infrastructure is annihilated. Communications are dark, roads are impassable. The Federal Emergency Management Agency, FEMA, is essentially flying blind. They need to know instantly where the worst structural damage is so they can deploy emergency resources effectively. Historically, human analysts would have to squint at thousands of aerial photographs, manually counting collapsed roofs.
Which would take weeks while people were just waiting for help.
Exactly. But using these space-grade AI vision models, analysts fed the post-hurricane satellite imagery into the system. The AI instantly detected and mapped 126,000 blue emergency tarps on damaged roofs across the island.
126,000 tarps pinpointed almost instantly.
Yes. That single massive data point allowed disaster relief teams to immediately characterize the severity of the damage across thousands of isolated local communities.
That is amazing.
It took the exact same visual processing power used to navigate a rover around Martian rocks and use it to direct actionable, life-saving human aid on Earth.
And it's not just disaster relief either. It trickles all the way down to commercial travel. NASA has a program called the Digital Information Platform, or DIP.
Oh yes, DIP.
They are using AI algorithms to analyze huge swaths of airspace data to streamline commercial flight routes. So the next time you're sitting on a passenger jet, an AI might be autonomously rerouting your aircraft to avoid turbulent weather fronts, save thousands of gallons of jet fuel, and get you to your destination safer.
All of it driven by computational logic developed for space travel.
Yeah.
It's a beautiful feedback loop. The extreme constraints of exploring the cosmos force us to invent far better, more efficient technology, which inevitably makes life on Earth safer and more resilient.
So what does this all mean? We started out looking at a terrifyingly massive deluge of data, trying to figure out how we could possibly make sense of a universe that is just throwing terabytes of noise at us every second.
And what we found is a solution.
Right. What we've discovered is that AI is the ultimate bridge. It is the tireless, hyper-vigilant assistant filtering through the glare of a star to find 6,000 new worlds. It is the brilliant translator turning the invisible infrared heat of a distant galaxy into a physical map that human eyes can actually understand.
And the pioneer mapping its own path across the Martian dirt.
Yes. And most importantly, it is bringing all those lessons from the stars back down to Earth, tracking our greenhouse gases, directing our disaster relief, and helping us protect our home.
I think that is the core takeaway here. We live in an era where we are constantly told that we are suffering from information overload, that technology is just cluttering our minds.
We hear it all the time.
But these tools prove the exact opposite. When applied to the physical universe, technology can actually clarify our reality. It distills the chaotic noise into profound meaning.
It finds the firefly in the spotlight.
Exactly. But this raises an important question, and it's something I want to leave you, the listener, to really mull over tonight.
Oh, I like where this is going.
We talked about the SETI Institute earlier. Right now, at the Allen Telescope Array in California, SETI is actively using AI systems to search for extraterrestrial intelligence.
Looking for signals.
They are training machine learning algorithms to listen to the roaring cosmic radio noise, looking for anything that resembles a technosignature, a mathematical signal or a pattern that couldn't possibly be generated by a pulsar or a natural phenomenon.
Because the AI can hear patterns in the static that our human ears and traditional programs just can't pick up.
Precisely. So if we follow this trajectory to its logical conclusion, it is highly probable that an AI system will be perfectly timed to be the first entity to actually detect a confirmed signal from another intelligent world.
Wait, really?
Yes. The human won't hear it first, the machine will. So the provocative thought is this. If an artificial intelligence is the very first thing on Earth to detect an alien intelligence in the noise, should an artificial intelligence be the first thing we use to reply?
Oh, wow.
And if we do hand over the microphone to the machine, what exactly would it say on our behalf?
Wow, that completely changes how you look at the sky. You go out tonight, you look up at that peaceful, still, quiet night sky, and you realize it is actually a roaring torrent of data. And somewhere out there, an AI is sitting quietly, sifting through the roar, waiting for a voice to speak back. Thank you so much for sending in the massive stack of sources for today's deep dive. Keep asking those big questions, keep feeding your curiosity, and whatever you do, keep looking up.
This has been Better Side of the World. And somewhere tonight, something good is still happening.